Okay, folks, so here's another example problem. And in this example problem, it's going to want us to calculate the pH of a buffer solution that I have made. So let's take a look at the question and see what it wants me to do and how to solve it. So the question is going to say, calculate the pH of a solution formed by mixing 250 mils of a 0.15 molarity HCHO2 with 100 mils of 0.20 molarity LiCHO2. And the Ka for HCHO2 is 1.8 times 10 to the negative 4. Woo! That's quite a bit of word, right? I mean, it seems like they bombarded me with all of these chemical formulas and all of these numbers and all of this terminology. And the very first thing that I have to make sure of is that I have to make clear what is an acid, what is a base, and why is Ka important in the first place. That's really what this is all about. Okay, so let's dissect the problem a little bit before we go through and start talking about how to solve the problem. Because if I don't know the pieces and the parts, I'm not going to be able to get an answer of the pH for the solution. All right, so first, this is a buffer. I probably know that because I'm working in a buffer section or a buffer lecture portion of a class. And if I did not know that this was a buffer, I know, just with experience, that this problem includes an acid, a base, and a Ka. So anytime the problem gives me a base to work with, an acid to work with, and a Ka, which is also very similar to a pKa, then I'm probably going to interpret this as a buffer solution. In addition to that, it also says calculate the pH. All right. Now, I want you to go back and think about what pH is. pH is equal to the negative log of the hydrogen concentration. The problem, though, folks, is that I can't use this equation for this problem. And the reason is because there's more than just an acid that's in the question. If it only gave me acid and that was it, then I could use that simple pH equation in order to solve this problem. But that's not how this problem is set up. This problem includes an acid. That's great for me, but it also includes a base. And I'm going to have to bring that into the picture. I can't ignore it. I can't leave it out. And that's one of the reasons they put it in the problem. So this simplified pH equation, not going to work for us. We're going to have to choose something else. So what we choose is something that we call the HH equation, and that's the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is used as a very shorthanded way to calculate buffers. Now, we can go back again and use ice charts, right? Starting concentrations, ending concentrations, the change of concentrations throughout the reaction. But this is quite a bit of math, and I don't want to do this for fun, and you don't want to do it for fun. So instead, we use Henderson-Hasselbalch in order to do this. So the Henderson-Hasselbalch equation says, if you want to calculate the pH, well, the pH is equal to, and they give me this pKa value plus log of something. And this log of something, they typically write as A minus over HA. And the reason they do this is because they're trying to give you a little bit of insight that A minus is really the base and HA is going to be the acid that's in the problem from up above. One of the other pieces that we're going to have to pull through is pKa. And pKa can be obtained from that question, folks. It's right there in it. It's not labeled as pKa, it's labeled as Ka, but it will allow me to calculate the pKa. So again, I want you to go back and I want you to think about pH equation. pH equals negative log of H plus. Typically, everybody can spit that out. I mean, you've memorized it, you've regurgitated it so much that it just comes natural, like riding a bicycle. Well, if you just said pH equals negative log of H, then guess what, folks? You know how to calculate pKa, because pH, just like pKa, is negative log, but instead of H plus, it's the negative log of Ka. That's the relationship here. It doesn't need to be complicated. So if this is in reference to hydrogen, then this also should be in reference to hydrogen. If this is in reference to Ka, then this is in reference to Ka. All this P function basically means is negative log. Whenever you see P, whether it's pH or pKa or PBs, it doesn't matter. P represents negative log. So pH equals negative log of H plus, pKa equals negative log of Ka. So the problem gives me Ka for this HCHO2, and it gives me this number. So to calculate my pKa that I need for this problem right here, I need that value. The problem doesn't do me a favor. It doesn't give it to me. I'm going to have to do it myself. So I'm going to take negative log of parentheses 1.8 times 10 to the negative 4. So if I plug that into my calculator and I just key it in, just like it's written, negative log, open up your parentheses on your expensive, close to $200 calculator, 1.8 times 10 to the negative 4, and close that parentheses up, key it in just as it's written, and you hit enter on your expensive TI-84 or whatever you have, then pKa, you're going to find out, based on that calculation, is going to be 3.7447, and the decimals keep going. So we're going to round this off to 2 decimal places, and this basically means that the Ka, that's fine. Sometimes I need Ka, but I'm also going to write pKa here of 3.74. All right? So now I have that value that is a component to the Henderson-Hasselbalch equation. I can plug that into pKa at this point, and now I'm just going to have to figure out the concentrations of my base and the concentration of the acid. All right, so we are quite halfway there, but we are making baby steps in order to solve this problem. And we're dissecting it, folks, piece by piece. That's why we're doing what we're doing. All right, so check. I'm going to solve for pH. Ding, ding. There it is. And then check. I've just now solved my pKa value. Ding, ding. So there that is. And now I'm going to have to work on this log of base over acid. Okay. So in order to do this, I'm going to have to go up to this problem, and I'm going to have to figure out which of these species is the acid and which of the species is the base. This is a very easy thing to do. I'm going to kind of give you some tricks, and these tricks, I hope, are self-explanatory in a way. It says the Ka for HCHO2, right there it is. All right, well, Ka basically means A, acid, and the Ka is dissociation constant. So that means that this material, this compound, this molecule, it's going to break apart. It will disassociate itself. If you disassociate yourself with someone, what do? You step away from them. You no longer hang out with them. You're no longer friends with them. And the acids are the same way. They're BFFs, and they're getting ready to split ways. So one of the friends, hydrogen, is going to be kicked to the curb, which is the definition of an acid. And that needs some coaching. That needs some persuasion in order for the acid molecule to spit the hydrogen off. It does have a little bit of heart. It doesn't want to necessarily kick off the hydrogen just like that, but it does have a tendency to do it. And the Ka will tell me how much persuasion it needs in order to kick the hydrogen off and by definition become an acid. So it says the Ka, acid dissociation constant here. This acid dissociation constant for this. That means that this is the molecule that's the acid, which means that this molecule that is written prior is going to be acid, and this concentration has something to do with it, and that is the HA that is in the Henderson-Hasselbalch equation down here at the bottom. Okay, well, what's this LiCHO2? This is the base form. That base form is also listed because that's how we make a buffer. We need a very weak acid and a conjugated base to come along with it. So this base is going to be filled in for A-. So here is base and here is acid, and now I have identified which is the acid and which is the base. So the Ka will tell me what species is acting as an acid because that's why it has a Ka value. Or, if I didn't know that, I could simply look at this and say, oh, look, this has a hydrogen in the front, and this has lithium in the front. The definition of an acid typically shows me hydrogen listed in the front. So HCHO2 is hydrogen in the front, which means it's an acid. So this is one of the ways that we just kind of give you some of that information in a chemical nomenclature fashion that we can make some assumptions with many, many different times. So I've got these two concentrations, but folks, I've got an issue here. And the issue that I have is that I can't just simply put in 0.15 molarity here and 0.20 molarity here on the top. Now, you're probably saying, well, why not? Because the question tells me that it's 0.15 molarity, and it tells me that it's 0.2 molarity. Well, it does, but they're misleading you. And the reason that they're misleading you is because you're leaving out some parts of the problem. Notice we took 250 milliliters of that 0.15. And we took 100 milliliters of the 0.2. And then we mixed it together in a container. So when this is mixed, in a sense, I've somewhat diluted both of these, haven't I? I've taken 250 mils of this one and 100 mils of this one, and I've mixed them together in a container, and that gives me a total volume of 350 mils. So I have diluted the 0.15, and I have diluted the 0.2. And I have to correct for that in the Henderson-Hasselbalch equation. All right, so on the next page, we'll kind of clean this off a little bit, and we'll flip back and forth, so don't get dizzy on me yet. But I have this HCHO, right? So this is formic acid. If you didn't know what that was, that is formic acid. It's the acid that's in little bitty ants. So when they bite you, if you're outside playing in the dirt, then those ants are injecting formic acid into your body, and that's what causes it to burn, and it feels pretty bad when it does it. So that's formic acid. Well, there is a base form that this problem is bringing in, and that base form was this lithium, right? LiCHO2. All right, so LiCHO2. And here, I kind of made a boo-boo. Let me go back and just clean that up and shift that 2 over a little bit. All right, so HCHO2 and LiCHO2, and this is going to be my lithium formate. That is the name of that compound. So this is the base, and this is the acid. Now, if I go back to the problem, it tells me that I've used 250 mils of the acid at 0.15 molarity concentration. All right, so 0.15 molarity concentration, and I've used 250 mils of that. And then for the base, it looks like I've used 0.2 molarity for that one. So let's write the concentration over to the side. Paper is meant to write on, so don't feel bad to write on it. Put the effort in, scribble on it. That's why you've purchased notebook paper. You might as well use it. And we've got 100 mils in total for it. All right, so here's the breakdown. I now know which one's the acid. I know which one's the base. If I can figure this out, I'll know how to put this into the Henderson-Hasselbalch equation. All right, so let's start with the very first one. So with the very first one, I'll work with the acid part. So it looks like I have taken my initial concentration, 0.15 molarity. And I have taken 250 milliliters of that. That is CV equals, well, I want to know what is my new concentration after this is over with. And that new concentration will have a total volume of 350 mils. So CV. So this goes back to kind of basic general chemistry, working with the dilution problem. I've taken 0.15 molarity solution and I have diluted that to a total of 350 because I'm getting ready to mix two pieces together. Okay, so if I plug this into the calculator, and we'll do it baby steps, folks, that way you can follow through with me. So 0.15 times 250, this is going to be 37.5 equals 350 times x. So I'll take 37.5 and I'll divide by 350 in order to solve for x on its own, right? You always do the opposite of 350 times x. You're going to divide by 350 to get x by itself. And what you do to one side, you've got to do to the other. So that means that my concentration here is 0.1071. Now I can round these numbers off, significant figure them, whatever the case is. I don't really care about that right now. The only thing, I'll keep about 4 or 5 decimal places typically in these problems. And then at the very end, I'll round them off to make them appropriate. So this means that after this dilution takes place, if I'm in a laboratory and I take 250 mils of that acid and put it in a container and dilute it to a total of 350, then this is my newfound molarity that I'm going to have in reference to the acid concentration. All right. Now, number 2, I now need to work with the base. And I do kind of the same thing here. It is another dilution problem, CV equals CV. So in this particular question, it tells me that the initial concentration of the base is 0.20. And I've used 100 milliliters of that material. Okay, well, what is the concentration of that base if I take it to a total volume of 350? Okay, so again, we'll do baby steps. There is my dilution equation. CV equals CV, initial concentration, initial volume. What is the final concentration of the final volume that I have added together? All right, so 0.2 times 100 is going to be 20. So maybe you didn't need a calculator at all. I hope you didn't. So 20 equals 350x. So that's 350 times x. So to get x by itself, you divide by 350. And I'm going to take 20 and I'll divide by 350. And x is going to be 0.05714. And that is in terms of molarity yet again. So this is the concentration of the acid after I've mixed the two together. This is the concentration of the base after I have mixed the two together. All right, so we're getting closer. We're getting closer. All right, so now what we're going to do is I'm going to erase some of this stuff. We'll leave some of it on here. That way you can keep following through. And then I'll get rid of the dilution step. We know how we've derived that number now, so I'll leave that there. And then I'll do the same thing here for the base. So we need to go back to our Henderson-Hasselbalch equation now. And that HH equation said pH is equal to my pKa plus the log of the acid or the base over the acid. Now, you need to keep in mind that these are really in reference to concentration of bases and concentrations of acids in terms of molarities here. If your question did not give these to you in molarity, you have to get them into molarity. So for instance, if they told you gram of acid that you've weighed out, or base of acid that you've weighed out in grams, or maybe even in milligrams, you're going to have to convert that into mole. You're going to have to know how much of that you've made, so that will give you volume, and that will give you molarity. It is always molarities that go into the Henderson-Hasselbalch equation. This problem was very good to me, because it told me molarity straight out of the bat. It did. I didn't have to do any work to them other than diluting them. But if it did not, and they really wanted me to work for those points on an assignment or a test or an exam, then I would have to calculate that molarity on my own. And that goes back to moles over liter. All right, so the pKa we did before, that pKa was 3.74. So 3.74 plus the log of parentheses divisor. So the concentration of the base, well, we just calculated that out, 0.05714. And the concentration of the acid here is 0.1071, and I'll close those parentheses up. So I'll take 3.74 plus the log of, and again, let's do baby steps. Don't rush all of these at one time. So 0.05714 divided by 0.1071, we kind of rounded that off to 4. So we'll hit enter on our calculator, and we'll end up getting the 0.5335, and I'll keep another one 4, just for fun. All right, so now I'm going to take 3.74 plus, and I'm going to take log, key that into your scientific calculator, 0.53354 to get an actual value at this point. And this turns out to be a negative 0.2728. So I'll take 3.74 plus a negative 0.2728, and I will end up getting 3.46, and I will write a really tiny 7 after the 6. So if they want me to round this up, this will be 3.47. And if they want me to keep it the way it is going to be a 3.46. So basically what this question is saying is that if I go into a laboratory and I take this acidic solution, 250 mils of it, and this basic solution, 100 mils of it, and I mix them together in a beaker, and I take a pH probe, and I stick the pH probe down into that solution, the theoretical pH that I should get on that pH meter is 3.46 to 3.47. If it is not, then I've made that solution the wrong way. Or if it's not, then the concentrations of the acid or the base, or maybe both, are completely off. But this gives me a theoretical pH value that I can then take and make the solution in a lab, check it with a pH probe and a pH meter, and hopefully, if I've done my job the right way, that solution would have a pH of 3.46 or 3.47. Now, one final takeaway that I want you to kind of understand from this problem is that the original pKa of just the acid alone was 3.74, right? This is the pH of when formic acid begins to spit off the proton. So at pH of 2, formic acid keeps the proton, the hydrogen. At pH of 3, formic acid keeps the proton. It keeps the hydrogen. At pH of 4, well, we're now over the pKa value. Formic acid looks at hydrogen and says, ew, I don't like you anymore. You're going to be kicked to the curb. And then hydrogen, ping, goes away. So 3.74 is kind of the number of pKa. That's what pKa represents. Well, look at this problem. We started off at 3.74 and we're now down to 3.46. We have gotten more acidic in a way, right? I mean, think of the pH scale. The pH scale goes from 1 to 14. It actually goes below a 1. It goes negatives if it needs to, and it actually goes above a 14. We can get pHs of 20s if we want, depending on what we're using. But typically it's 1 to 14. That's what we talk about all the time. So 3.7 and 3.46, if you were given a question that said, which one's more acidic? You would say the one with 3.46 pH. Well, hopefully that makes sense. We have gotten more acidic. And one of the reasons is look at your concentrations here. We did concentrations of the base. We did concentrations of the acid. And we mixed more acid here than we did base here. So it doesn't quite make sense that this would go more basic, does it? Because we didn't add as much base as we did acid. So if this problem was reworded, and if the problem gave me new numbers, and those new numbers had a higher concentration of the base, then my pKa value from where I started would go up in reference to the answer. Because, in other words, what I'm saying is that if this question, and we broke it down the way that we did, we had more base that we mixed into that container, then my pH level would go higher now than the pKa value. And that's because we're going more basic, because we have more base as far as concentration goes. All right, so this is the question that they gave me here in this example. We spent 28 minutes talking about this. We broke it down piece by piece, step by step, but hopefully you're becoming a little bit more familiar with the Henderson-Hasselbalch equation. So HH equation, Henderson-Hasselbalch, pH, pKa, log of base over acid. It is one of those equations that you absolutely have to memorize. We use it so often in a laboratory that it is one of those things that we have to go to almost all the time. And instead of wasting time to look it up, folks, we use it so much that we just get used to it. All right. Now, again, there are other ways to solve this problem. The other ways to solve the problem, if you've taken a general chemistry course, is through an ice chart. But quite honestly, you should get about the same number using an ice chart as you did the Henderson-Hasselbalch equation. That's the purpose of using this equation as far as making a buffer goes. All right. So with that said, this video is now done. You'll probably will get more videos with more examples, but here is another type of buffer problem that you might see in a chemistry course or in one of our courses or in the laboratory environment.